Morning, students. Today we're in a new chapter. The name of the chapter is feedback. Let's first understand what is the concept of feedback. I have seen in your curriculum there is not much of a detail. Basically, concept is in your curriculum. So we shall limit our discussion in concept only. Of course, let me give you a caution. In case you are in a hardware industry, then feedback is a day-to-day activity, and you will have to learn a lot more on this. Anyway, coming to the feedback, here I have shown you, I think you can see, this is a signal source of 1 kilowatt signal source. I have supplied a voltage of 0.5 volt RMS, and this is an amplifier of gain 10, right? Now, let's run this system. We shall see how it works. So this is the red line is the output, blue line is the input. And here, of course, the scales are different. Output scale is 5 volt per division. Input scale is 500 millivolt per division. So that is scale is 1:10 ratio, and both amplitudes show same. So I can say that there is a 10 times amplification, right? So since it's a amplifier, inside circuit you don't bother. Say it's a black box amplifier of 10. Now say I have given zero point 0.5 volt input, gain 10. So here you can see the voltage output is 5 volt, right? Now the here I have made a potential division of 9.5 kilo ohm and 500 ohm. That means it's a total is 10 kilo ohm and this is 500 ohm. So this is 1:20 ratio. 1:20 ratio, right? So this is total 5 volt and it is 0.25 volt. So also 1:20 ratio. So 1/20th of the output, I can, if I close this switch, I can give it to the input, right? And this is a addition amplifier. Now, if I give to the input, mind it, the output red line is out of phase, 90 degree, 180 degree out of phase of the blue line. That means it is in phase opposition, right? That means this 1/20th of the output will be subtracted from the original input Vs. So once again, I repeat, what is the concept? A part of the output is input in opposition, in subtraction, which will reduce the input. Now, if I do that, then what happens? Then what will be the gain? So I close this switch, I run it once again. Now I see the red line amplitude has dropped and it has become 3.385 volt. Input was 5 volt RMS. So if I calculate, so it becomes 3.385 by zero point 0.5, 3.385 by zero point 0.5. The gain has become 6.77. So the gain has reduced. So concept is a part of the output is fed back to the input opposition, or theoretically said, a part of the output is subtracted from the input. In that case, the gain of the amplifier reduces. This concept is called feedback. That means feeding back the part of the output to the input. Now, you may ask what is the use of such a technique where the gain is reduced? Now, to understand why this technique is used, although it reduces the gain of the amplifier, we shall go into the theoretical aspects of this. First, I have shown you what is feedback, right? Then you shall go to the theoretical aspect. I'll change this screen for a moment. So just wait, I'll change the screen. Now I come to this screen, right? So this is a feedback. Chapter is feedback. Now we shall see. It is a technique of feeding a part of the output back to the input. This is feedback. Now, if the feedback is negative, the gain reduces. But this is the most important part. But all the important characters of the amplifier improves. Important characters means its stability or instability, its bandwidth, its input impedance, its output impedance, everything improves. Everything improves at the cost of reduced gain. So, if in an amplifier, suppose you have an audio amplifier, and at the last stage, if you use a feedback stage, then what happens? Gain of the amplifier becomes very stable. Its variation of the gain due to temperature, age, etc., is much reduced. Then we shall see how it really happens. This is the idea. Schematic diagram. I showed you the circuit diagram. This is the input Vs supply voltage. Goes to the positive end of the addition circuit, and this is the V in, which actually goes into the amplifier, whose amplification factor is A. This is the output. So VO is equal to A into V in. And this output is tapped out from here, where again a multiplication factor is beta is applied. Beta is of course less than 1, 1/10th, 1/20th, something like this. So V0 multiplied by beta is fed back to the input in negative polarity. This is negative feedback. Now, it is also possible to positive polarity, which is a positive feedback. But effect of positive feedback is completely different. It's a completely different chapter altogether. We shall see if it is in your curriculum. We shall see a little bit of that later on. Today, we are limited within the negative feedback, where the part of the output is subtracted from the original input. In that case, this VO, A times V in, right? And what is V in? Is Vs minus beta VO, which makes AVS minus A beta VO. Now, if you bring A beta VO to the left-hand side, it becomes VO multiplied by 1 plus A beta is equal to AVS. So, VO by Vs is A divided by 1 plus A beta. It's a very simple relation. If the open loop gain of the amplifier is A, then closed loop gain, that means the gain with the feedback loop, or sometimes they also call it transfer gain, that means final output divided by initial input, is A upon 1 plus A beta. This relation is very easy to remember, and you have to remember this relation, that in case of negative feedback, the closed loop gain is A upon A. What is A? A is the open loop gain of the amplifier itself, and beta is the feedback factor, right? Now, we go to the next step. Some topologies. In fact, four different types of feedbacks are possible. I've seen these topologies are in your syllabus, although yeah, I think this is very theoretical, bookish. You just remember the diagram and just remember what is what. This is called voltage amplifier because this amplifier basically is a voltage amplifier. You remember, uh, time back we discussed four different configurations of amplifier. One is voltage amplifier, which is voltage input, voltage output. What is current amplifier, which is current input, current output. And there is a voltage to current converter. That means current output, voltage input. The transfer ratio is current divided by voltage. That is why it is called transconductance amplifier. It's a very bookish name, but nobody really uses this name. Everybody calls it voltage to current converter. There is another one which is current to voltage converter, where input is the current, output is the voltage, and transfer ratio is voltage by current. So it is called trans resistance amplifier. These are all bookish names, but in industry, everybody calls it current to voltage converter. Now, this is a voltage amplifier. Now, voltage amplifier, this is the input and this is the output. Now, the tapping that has been done here is the total output voltage has been taken here, right? This is output VO. So the voltage between these two lines is VO. There is a factor of beta. This is another circuit, and output of this is VF or feedback voltage is beta VO, where this is the schematic positive side, this is the negative side. And this is added here, given here. And if this is given, if VF is given in series with VS, and the polarities are like this, then obviously input is Vs minus Vf. So this is a voltage amplifier with voltage feedback and feedback in series. That is why it is called voltage amplifier with voltage series feedback. The series term applies here. It is in series, right? And voltage term applies here, that the output taken from the voltage, and original amplifier is a voltage amplifier. Next comes another topology, transconductance amplifier, where the input is a voltage, output is a current. At current output, obviously you have to take it in parallel, in shunt like this, because current has to flow from here to here, inside the circuit to inside the circuit. Current tapping cannot be done this way. Current tapping has to be done this way. In that case, this current IO flows through the feedback circuit also. And output of this feedback circuit is a voltage. And its amount is beta into IO. And it is again in series. So what will be the name of this? It will be series feedback, and feedback is based on the current. So current series feedback, and amplifier is voltage input, current output, so transconductance amplifier. So this remember this schematic diagram, and actually in industry, you will not get feedback amplifiers looking like this. There is a complex amplifier. By looking at the amplifier and investigating in the amplifier, you will have to find out what kind of feedback it is. Now, this is a current amplifier, where input is current, output is also current. And if I take a current feedback, then obviously feedback line will be like this. And output of this current, here output of the feedback circuit was, here feedback circuit input was current, output was voltage. Here feedback circuit input was current, output is also current. And if current has to be added in fan opposition, obviously the it will has to be connected in shunt. And so it is called current amplifier with current shunt feedback. Next comes transresistance amplifier, where input is current, output is voltage. Here, uh, feedback tapping is the voltage tapping, and output of the feedback circuit is current. So it will be, and since it's a current, it has to be added or subtracted from the input current. Of course, the connection has to be shunt connection. So this is a shunt feedback like this here, and feedback is based on the voltage, and amplifier is a transresistance amplifier. So these are the four basic topologies of feedback circuits. Next, effects of negative feedback. Now, to find out the effects of negative feedback on four different topologies of feedback circuit, it's a lengthy discussion. It's a lengthy discussion because there are number of effects, 5, 6 different effects, and it has to be multiplied by four different amplifiers. So it is a lengthy discussion, and which I find is not in your syllabus also. But I have given here the important outcome of negative feedback that you need to remember even in your BTech course. Closed loop gain is this AF, there's a feedback, A feedback, and A means open loop gain is 1 upon 1 plus A beta. So, of course, gain reduces, right? Of course, gain reduces. This is number one effect of negative feedback. Number two effect is gain sensitivity. This is important to remember. We have said that if you design an amplifier with feedback, then its gain sensitivity or sensitivity of its gain on temperature, aging, and component tolerance, etc., is much reduced. So your amplifier becomes a higher quality amplifier. How can you prove this? This is the basic equation, AF equal to A upon 1 plus A beta. Now we differentiate it with respect to A. If you do that, dF upon dA, this is the normal differentiation program of ratio when both numerator and denominator has your functions of A. Then this is equal to 1 plus A beta square. In the numerator, A beta gets cancelled, it remains only 1. This can be written upon A upon 1 plus A beta multiplied by, again, 1 upon 1 plus A beta into A. Now, A upon 1 plus A beta itself is AF. So we can write it AF divided by 1 plus A beta into A. So DF by DA is this. So we can write DF by AF, this AF with cross multiply, DF by A will be equal to divided by 1 plus A beta upon A. So what do we get here? Now, equation dF by A is a representation of partial change of feedback closed loop gain, right? Say 10% or 2% change of closed loop gain. And dA by A is the partial change of the open loop gain of the original amplifier. So if by any reason the dA by A is say 10%, so original gain of the original amplifier changes by 10%, then the gain of the feedback amplifier changes the 10% divided by 1 plus A beta. 1 plus A beta always much more than 1. So what we see, the sensitivity, sensitivity is much improved. So proportion of change in closed loop gain is actually proportion of change in open loop gain divided by 1 plus A beta. That means enhanced gain stability. This is number one point. Further, if you design in such a way that if you design in such a way that A beta is much more than 1, it is possible to design in such a way. Then A becomes A upon 1 plus A beta becomes A upon A beta becomes 1 by beta. That means if A beta is much more than 1, then F is equal to 1 by beta. What does it mean? It means that closed loop gain has nothing to do with A or the original amplifier. Closed loop gain depends only upon beta, that means the design of your feedback circuit. So the closed loop gain becomes independent of the open loop amplifier. A fantastic improvement. That means you have an amplifier, somebody else designed it, design a feedback circuit in, in such a way that A beta becomes much more than 1. Thereafter, the closed loop gain of the amplifier will have nothing to do with the original amplifier or its quality. It will depend only on the quality of your feedback circuit. Besides that, besides that, negative feedback reduces distortion due to non-linearity. Many components, particularly PN junctions, there is some non-linearity, which creates some distortion. Distortion is reduced. Next is A beta is much more than 1. Gain is independent of frequency because that means the gain of the original amplifier. It depends upon the coupling capacitors, emitter bypass capacitors, etc. But if your closed loop gain is independent of A, then your frequency altogether, that means you have an infinite bandwidth up to megahertz, gigahertz bandwidth, provided your feedback circuit does not have any reactive element. It has only, or if you can make a very good design of the feedback circuit, it has no reactive element, only resistive elements, then your amplifier closed loop gain becomes independent of frequency. You don't have to bother about the bandwidth. Amplifier. Now, I discussed earlier, the voltage amplifier, where input is voltage, output is also a voltage. Your voltage amplifier design should be such that input impedance is high, output impedance is low. Now, in order to design, if you not succeed in making it high or low, then if you add a feedback circuit, then input impedance automatically will become very high, output impedance will automatically become very low. This happens in voltage amplifier. Now say for current amplifier, where is current, output is current, where input resistance should be where input resistance should be very low, output resistance should be very high. Now feedback, if you have a feedback current amplifier, then input becomes very low, output becomes very high. automatically. Now, this is a lengthy process. There are many such variations available, but you need to remember in a voltage amplifier, current amplifier, or transconductance amplifier, or transresistance amplifier, the way you desire it about the input resistance and output resistance, you get exactly the same desired result with the help of a feedback. These are the basics of a feedback topology, which is in your syllabus. And as I said, we have discussed minded only negative feedback. Feedback can be positive also. And what happens if the feedback is positive, that we shall see later on in some other chapter. Now, what we shall do, we shall now go to we shall now go to test a feedback amplifier. That may be interesting for you. I'll change the screen at once again. Just hold on 2 seconds. The screen will change. Okay. To this screen of simulation software. Now I'll show you. This is a feedback amplifier. I hope you can see this. This is one stage of common emitter amplifier. Used to this amplifier, this is a power supply, this is a signal source, 1 kilowatt signal, this is input coupling capacitor, and there is a second stage of common emitter amplifier, which is coupled by a coupling capacitor, and this side is the out. Now, this is the oscilloscope, this is a distortion analyzer, this is a board plotter. I will make the complete test of this. Now, actual circuit is, feedback circuit is, point is connected here. Look at this now. If this point is connected here, then what happens? This is the output of the second stage, and it is connected to the load of 5 kilo ohm resistance. Now, from here, see, there is a 4.9K resistor, and it is a 100 ohm resistor. So total is 5K resistor. This is also a 5K resistor, right? When there is a 5K resistor, now see, this is 4.9 and it is 100, and total 5,000. So 5,000 by 100 means 1 by 100 means 50. That means beta or feedback factor in this circuit is theoretical calculation. But when we actually test this, we shall see it is not exactly 50, maybe 49, because all these components in this circuit have got their tolerances. So what we shall do now, we shall disconnect the feedback circuit, and this is a 5K resistor. We shall check this amplifier. This is now open loop amplifier. We shall check its various properties. So this is the oscilloscope we need to see the waveform. This is the distortion analyzer. As I said, we must always check the distortion is not very high, and we run it. This is the output, right? Red line is the output, blue line is the input, but if it is so so low, you cannot see it. There is the input blue line. This is so low, you cannot see it. Now we see that distortion is less than 10%. As I said, distortion should be how much, that is your decision, but I have made a standard that for all testing, we must check that distortion is less than 10%. You can check it with distortion less than 5% also. because if I make one standard, then there is a similarity of testing. Now here I shall do one thing. Oscilloscope I shall remove. Distortion meter also I shall remove. For checking the gain, I shall connect the meter here. There is another voltmeter here. I, sh- I shall run it for a few seconds. Now here I say peak to peak output voltage is 9.03 volt. It means AC part, 9.03 volt, and input voltage is 2.83 millivolt. So gain becomes 9030 divided by 2.83. 2.83. Gain becomes 3190. So here I have listed the open loop condition, AA, 3190, right? Now, what is the input resistance? Input voltage is 2.83 millivolt. I see input current is 110 nanoampere. So input resistance is 0.83 milli by nano, 110 ohm. That means it is 25.7 kilo. So input impedance is 25.7 kilo. I shall see the both plot to see the what of frequencies. I reverse the so that you can see it properly. The mid frequency gain is 72.566 dB. So 72 minus 3 is equal to 69.566. Upper cutoff 69.566, 69.566 is approximately 120 kilohertz. I have written 119 kilohertz, so I shall correct it to 120, 120 kilohertz. And lower 69.5, lower cutoff 9.5 is 124 hertz. So lower cutoff 124 it shows 124 hertz. Got gain and output impedance we have to measure. If we have to measure output impedance, then we should. There are many methods. I shall take my method. The source I shall disconnect. I shall connect another source here. I shall connect another source here. And from this source, I shall supply to the system from the output side, right? Supply to the system, and then I shall measure the voltage and current of this. I shall run it. I see if I supply the system from the output side, then peak-to-peak voltage is 2.83 millivolt and peak-to-peak current is 1.65 microampere. So impedance from the reverse side is 2.83 millivolt divided by 1.65. 1.65, so many kilo, so 1.7 kilo. So it is only 1.7 kilo, as I have written. So what do you find? This open loop amplifier, when it is in open loop, gain is 3190, input impedance is 25.7 kilo ohm, output impedance is 1.7 kilo ohm, lower cutoff frequency is 125 hertz, upper cutoff frequency is 120 kilohertz. Now, what do you want in an amplifier? You want amplifier gain should be high, but as we have found out, in feedback, gain will low down. You always want higher and higher. Output impedance is always want lower and lower. Want lower and lower. And upper cutoff frequency, you always want higher and higher. Now let us see what happens if we connect this feedback window. And also we connect this here. The gain will reduce, of course. So we'll do, since the gain has reduced, we shall increase the input. First, let us see what is the output. Output is the red line, which is very, very small. We shall increase the input. Now, output becomes higher. Input also becomes higher. Right? This is the output input. What is the distortion? Distortion is less than 1%. Right? Now, let us check the various parameters. I'll switch off the oscilloscope. We shall switch off the distortion meter. Then we shall now put the probes. This is the voltage probe. This is the current probe. And we need another voltage probe here. Run once again and see the meter readings. We find now the voltage is 6.79 volt output peak to peak. Input voltage is 141 millivolt. So what is the gain we got? 6.79 volt, 6790 divided by input is 141, output is 6790 is 141, 140, in one is the input. So 1 point something. So this gain of feedback amplifier is 41. So gain has reduced as we expected. How much it has reduced? We have seen that its beta factor is 50. So it should have reduced by 3190 divided by 50. It should have been 63. But what we got is 41. That is because the tolerances of various components and also the reactances. Right? Anyway. Are in. Input voltage is 141 millivolt. Input current is 4.03 microampere. So milli by micro is kilo. So 141 divided by 4.03. Input impedance now is 35 kilo ohm. This is 35 kilo ohm. So see, input impedance was 25.7 kilo ohm. It has increased to 35 kilo ohm. We always want input impedance to be higher. Now let us see the frequency cutoff bands. Here, now my mid-band frequency, mid-band 33.831. 33.8 minus 3 dB is 30.8. If we go to 30.8, 30.8, we have to find out 30.8 something. So is 10.98 megahertz. So this has become 10.98, say 11 megahertz. Okay. Earlier open loop gain, upper cutoff was only 120 kilohertz. It has increased by 10 megahertz. This is a fantastic improvement. And what is the lower cutoff? Midband 33.8. Lower cutoff is, I'll go to 33.8. 33.8. It is something like 5 hertz. 33.319, 33.8, 34. It's something like 5 hertz, right? So his lower cutoff is now only 5 hertz. So lower cutoff frequency of the open loop amplifier was 124 hertz. That means very, very low frequencies were cut off, but now the lower cutoff is at 5 hertz. This is a fantastic improvement. Lastly, let us see the output impedance. Right. I'll once again disconnect the input source, connect a source from the reverse side in the output, connect a voltmeter here, and connect a current meter here. Hence, earlier was 1.7 K. Let us say how it is now. Now, the source voltage is 2.83 millivolt and current is 83.6 microampere. So milli by micro is kilo. So 2.83 divided by 83.6. 83.6 kilo ohm, which is 0.033. That will only 34 ohm. So output impedance was 1.7 K. We want always it lower. It has come down to 34 ohm, right? So you see, negative feedback. I have shown you an actual circuit. So now you should believe in the theories and you should also believe in me that the gain reduces approximately by the feedback factor beta or 1 plus A beta. 1 plus reduces, but all parameters of the amplifier, it improves the desired side, right? So this is how a feedback amplifier works. By your, what should I say, by your bad luck or good luck, if in case you get a job in the hardware industry, you will, or hardware electronics industry, you will face this kind of circuit almost day to day. And you have to resolve if there is a problem in the circuit. This is where I shall finish my lesson or my lecture to you on feedback topologies and feedback concept. In our next lesson, I think as per your syllabus, next lesson is on the effect of positive feedback. Okay? Till then, goodbye and have a nice day.